Hey everyone, today we're going to discuss sections 5.1 and 5.2. I'm smushing those two together because each one of them is one slide in our whole deck. The reason why 5.1 is one slide, slide 104, and 5.2 is another slide, is because both of the sections really deal with certain concepts in chapter 6 that we already went through in depth using one lens or one point of view. I find that lens to be much more useful when discussing trig ratios, and trigonometric concepts. Using the unit circle approach usually and more rarely helps people more, but with my experiences with a ton of the students that I've worked with, almost always people prefer the chapter 6 approach because the chapter 5 approach usually involves memorization of a bunch of values or derivation of a bunch of values using the unit circle. In my mind, it's much more useful to think about trig in the context of chapter 6 because that's how it'll help you memorize less but work out problems on a problem by problem basis. It gives you more of a steady state sort of approach to solve problems. So check out problems in chapter 6 more so than you do in chapter 5, and read through 5.1 and 5.2, but I'm going to give you guys the highlights today. So within 5.1 we're talking about the unit circle, and we sort of discussed this in 6.3 where I put up a unit circle on the board and I said that a unit circle is a circle that is centered at the origin, which means its center is at x, y is 0, 0, and it has a radius of 1. Now, that's an important thing to note, the fact that the unit circle has a radius of 1. So any line that I draw from the center to an outer point on the circle, from the center out, would have a radius of 1. So if I were to draw this line out here from this origin to this red point on the circle labeled x, y in two different colors, that line, the blue dashed line, would have a distance of 1. That would form an angle called theta between the positive x-axis and the terminal ray that we drew that connects with the circle. Now, we know that the equation of the radius would be, or to find the distance, would be, since it's a right triangle it's formed, the first leg squared plus the second leg squared, then square rooted. That's the distance formula. But here I know that the radius equals 1, so the distance equals 1. And I know that the x value of this point is equal to the distance from here out. That's the whole length of the line. So the length of this black leg of the triangle is x, so the leg squared would be x squared. The length of this leg of the triangle is the y value of the point, because that's how far I had to travel up from y is 0 to y, whatever that y value is, whether it's 3/4 or a half. I traveled x units out, whatever the x value of the point is, and y units up. So the length of this line is y. So x squared plus y squared should give me the distance squared. That distance is the radius of a circle that we know has a radius of 1. So it's equal to 1 squared. But we know that 1 squared is equal to 1. So the equation of the unit circle, x squared plus y squared, is 1, right? Then I say the circumference of the unit circle is 2 pi. If we travel along the perimeter of a unit circle, we stop at any point p of x, y. So if I stop at point P, I can call that point x, y. So wherever I'm traveling along the unit circle, even let's say if I stop here, that's a point that's x, y. That's known as the terminal point. So what would the terminal point be if we traveled a specific number of radians? I ask a question, what's the terminal point if we travel negative pi radians? Well, if a total circumference or arc length is 2 pi radians, because the circumference is pi diameter and the diameter of a circle with a radius of 1 is 2. Total circumference is 2 pi. That fits with our whole definition of the radius, the radian measure of an angle here is 2 pi radians, right? If I went pi radians or minus pi radians, I'd be going 180 degrees, and my terminal point would be here, negative 1 comma 0, for instance. So what this section does is it gives you a point that might lie on the circle, and then asks you to find the sine, cosine, tangent, secant, cosecant, cotangent of the point. Or they can give you one value of the point and ask you to solve for the other. For instance, if they tell you here we have a point root 3 comma 3 as the x, well, root 3 over 3, as the x value. If I know that there's a point that lies on the unit circle, a circle with a radius of 1, and the x value is root 3 over 3, whatever that x value is, the x value of the point is root 3 over 3, comma y. And I don't know what the y value is. This is what some of the homework questions might look like. Well, by the unit circle approach, I know that the x value squared, root 3 over 3, plus the y value squared should equal 1, because the radius is 1. So I technically have the x value, or one leg of the triangle. I don't have the y value. So we could use the unit circle approach and the equation of the unit circle to say solve for values of the terminal point. Tell me what y is going to be. So root 3 over 3 squared is 3/9, plus y squared is 1. That tells me that y squared is going to be equal to 6/9. And the square root of both sides is root 6 over 3. So the y value of the point is root 6 over 3. Great. So if I had any terminal point, any point here, and I knew one of the values, either the x or the y value, I'd be able to solve for the other one using this equation. That's one thing that you can do using a unit circle approach. But how does that fit in with trig? Well, last class, or I want to say at section 6.3, we discussed, okay, if I have a point that lies on my unit circle, I can form a right triangle, and if I needed the sine of that angle that's formed, that would be the opposite side over the hypotenuse, let's say. If I needed the cosine of the angle, that would be the adjacent side over the hypotenuse. Well, the hypotenuse here is 1. So it's the opposite side divided by 1. The hypotenuse here is 1. So it's just the adjacent side divided by 1. Now what is the opposite side equal to? Well, it's equal to the y value of the point. So the sine of theta is equal to y over 1, or just the y value of the point. The cosine of theta is equal to the x value of the point. So that's how this fits with trig. Because if I were to say, okay, we have a point root 3 over 3 comma 6 over 3. So you know what the y value is now. Root 3 over 3 comma root 6 over 3. That's the x and y value of the point. You had an angle theta that was formed. Please tell me what the sine of theta is going to be. Okay, well the sine of theta is supposed to be the y value that we just found. It's root 6 over 3 divided by 1. Opposite over hypotenuse. Well, the radius is 1, so I don't have to divide root 6 over 3 by 1. What would be the cosine of theta? Well, that's the x value of the point. Root 3 over 3. What would the tan of theta be? The tan of theta is the y value over the x value, as we discussed in section 6.3. So I could find the y value, which is root 6 over 3, and divide that by the x value, which is root 3 over 3. And we learned about complex fractions. We learned that we can divide complex fractions by multiplying by the reciprocal. So root 6 over 3 times the reciprocal of the denominator would be root 6 divided by root 3, or just rad 2. So the tangent of this angle would be radical 2. And you should remember this based on our radical properties that we learned in class in chapter 1. So the unit circle approach is one that still uses stuff that we learned in section 6.3. That stuff told us, okay, since the radius is 1, the xy values of the point, using the same triangles or right triangles built in a circle, will give us opposite over hypotenuse or adjacent over hypotenuse. So we're still using triangles, we're still using SOHCAHTOA, but we put them in context of a circle with a radius of 1, so that then we can say that the sine of theta is the y value of the point, because y divided by 1 is y. The cosine of theta is the x value of the point, because adjacent over hypotenuse, or x over 1, would just be x. 6.3 though went a bit further, and your slides in 6.3 told you what would happen if the radius were not 1. If the radius were larger, let's say, if the radius of the circle were 2 or 3, it went further. It said, okay, if the radius is 2, we're still building a right triangle inside that circle. And we're going to use opposite over hypotenuse. So the sine of theta would be opposite over hypotenuse. The opposite is the y value, and the hypotenuse is the radius. So that's why 6.3 told you that the sine of theta is y over r, not just y over 1 or y. Because outside of the context of a unit circle, when the radius is not 1, you can't just say the sine of theta is y. The sine of theta would be y over r. Alright? So that's why I think 5.1 isn't as necessary or isn't as useful. You're still using right triangles. You're still putting right triangles inside of a circle. So we're not doing these things exclusively of one another, right? The extent of usefulness, as I said earlier, of this unit circle will be the fact that we can evaluate things like the cosecant of 270 degrees. And I'll give you that as an example of something that's not on your slides. If we had to do the cosecant of 270 degrees, well, you would end up saying, okay, 270 degrees, this is 90, 180, 270, boom. 270 degrees is on an axis. I can't draw a right triangle between the y-axis and the x-axis that would be acute. It would be a 90-degree angle. So what we can do here, since it's one of the 4 points that I discussed with you, it lies on the unit circle. I know that the xy point here is 0, negative 1. So since the cosecant of 270 is 1 over the sine of 270, it's the reciprocal function, and the sine of 270 is equal to the y value at 270, which is negative 1. The cosecant of 270 would be 1 over negative 1, or just a negative 1. So in my mind, that's why the unit circle is useful. It's useful because we can evaluate values at any of the 4 points that lie on the circle and on one of the axes. Further example, if I wanted you to find the sine of 90 degrees, you can say, okay, this is the point 90 degrees, this is the point 0, 1, the y value of the point of 0, 1 is 1, so the sine of 90 degrees is 1. And that's why I find the unit circle useful. Next, we're going to go on to 5.2. So I start off slide 105 by saying a part of this section is based off of things that we skipped in 5.1. So I briefly touched on terminal point. What exactly is a terminal point? A terminal point is, if we draw out a unit circle, a circle with a radius 1 centered at 0, 0. If let's say that was a terminal point, this is my initial ray, this is my terminal ray. This would technically be angle theta, but it is not an acute angle. We have a point P of x comma y. And if I were to draw a right triangle here and call this a reference triangle, for instance, the y value of the triangle and the x value of the triangle would clue me in as to values on the terminal point. And we still know that x squared plus y squared are the legs of the triangle squared and added, because the x value of the point is the x distance, the y value of the point is the y distance traveled, and the sum of the legs squared equals the distance of the hypotenuse squared. 1 squared is 1. So we're saying we can use this terminal point to find the trig ratios. But again, to my point, if I took the sine of this theta bar, I would have to take into account the fact that sine is opposite, which is positive, over hypotenuse, which is positive, so sine is positive in quadrant 2. But if the terminal point was here, for instance, and I needed the sine of this value, well, theta would go all the way around, theta bar would go here, and now the y value is negative, but a negative number squared plus this number squared would still give me a positive value, but I know that the y value of this point is negative. So whatever that point x comma y is, I could always use the y value of the point, right? I could always use the y value of the point here to get the sine of theta, the sine of the angle. The problem is, if I don't know y, if I knew x and I plugged it in here, I'd get a positive value for y. You have to use your brains to say, hey look, I'm underneath the x-axis. It's not going to be a positive y. If I were to get y squared equals a half, I know that y has to be plus or minus the square root of a half. Right? So plus would have put the point up here, plus square root of a half. Minus square root of a half would put the point here, and that's where we are. So that's what you guys got to sort of keep track of. Again, in my mind, 6.2 and 6.3 do a better job in putting together information that would help you understand reference angles, reference triangles, and how to find the value of sine, cosine, tangent, cosecant, secant, cotangent of any angle. Draw it out, find the reference angle, see if it's positive or negative, if it being the trig ratio is positive or negative in that quadrant, and solve for the value of the reference angle. Let's say if we had sine of 120, we'd be using sine of 60 plus the sine of 60 instead of that. And we did several examples in 6.3 like that. I like that more than the method used in 5.2 with unit circles. And again, I've sort of broadly explained to you how to do it here with unit circles in 5.1 and 5.2. You're going to get homework on it. If you have questions, please reach out. But I personally prefer the other methods used. You can even use the other methods to sort of answer these questions. And if you have questions, please feel free to throw them my way. On slide 105 though, I do point out the one thing that I didn't cover yet in these sections that is somewhat important. Even or odd properties. I told you they'd come back to haunt you. So when we discussed even or odd functions, we discussed a function like f of x that could be x cubed minus 7x squared plus 4, and I asked, is it even, odd, or neither? Well, in order to test, you'd have to say, okay, is f of minus x equal to f of x? Or is f of minus x equal to minus f of x? In this case, the function is even. In this case, the function's odd. Same thing in trig, my people. There are even or odd functions within the trig world. Cosine and its reciprocal function, secant, are the only even trig functions. For odd functions, we have sine and its reciprocal function cosecant, and tan and cotangent. And I'll work out a problem for what exactly this means. You have formulas here that will tell you the cosine of a negative angle t will equal the cosine of the positive angle t. That's the definition of being even right here. That was our initial function rule. If I negate the input, I get the same thing as if I had a positive input. So if I asked you to find the cosine of negative, let's say I asked you to find the cosine of negative 30 degrees, that would be the same as the cosine of positive 30 degrees. I'll give you another angle. The cosine of negative 120 degrees would be the same as the cosine of positive 120 degrees. And it's a pretty cool mini example, and I'll show you why exactly this is true. But this would only be true for cosine and secant. If I negate the angles for sine, it's not going to be, sine of negative 120 won't equal the sine of 120. Sine of negative 120 is going to equal minus the sine of 120. And we'll see that as well. We have two examples here, we can work through them. I have cosine of minus pi over 4, but I'd rather use cosine of minus 120. So what does that look like? Cosine of negative 120 degrees. My bad, the degree mark goes there. So how would I do that? Well, draw out my angle. Negative 120 degrees goes clockwise. It ends in quadrant 3. Theta is negative 120. I can't draw a triangle here. I need a reference triangle. Where's my reference angle going to be? Theta bar is going to be right there. What is theta bar going to be equal to? 60. So my reference triangle is 60 degrees here. And I know in quadrant 3, all students take tangent is positive. So cosine of negative 120 is going to be minus cosine of the reference angle 60. Right? It's going to be off by a plus or minus. In this case, since cosine is negative in quadrant 3, right? We know that we're going to negate the cosine of the acute angle 60. Well, what's the ratio of sides of a 30, 60, 90 triangle? It's x opposite 30, x root 3 opposite the 60, and 2x opposite the being the hypotenuse. So cosine is adjacent over hypotenuse. It's minus x over 2x. Or it's equal to minus 1/2. Now I could punch that into my calculator, find the cosine of minus 120. But since I'm telling you cosine is an even function, let's find the cosine of positive 120 right next to it. What would the cosine of 120 be equal to? Let's draw it out. 120 degrees positive goes into quadrant 2. So theta is 120. Well, theta bar would again be 60 degrees, but in quadrant 2. So cosine of 120 equals, here's 60 degrees, in quadrant 2, all students. Sine is positive in quadrant 2, cosine is negative in quadrant 2, and it's equal to minus the cosine of 60 all over again. So the reference angle is 60 here, the reference angle is 60 here. Cosine is negative in quadrant 3, so I get negative cosine of 60. Cosine is negative in quadrant 2, so I get negative cosine of 60 again. So the answer is going to be the same. I have the same triangle. It's going to be minus x over 2x, or minus a half. So I see that by actually negating my input value, cosine of a negative angle, I have the same impact as dropping that minus out and getting cosine of positive 120. And we see that here. It would be the case for the cosine of any negative angle. The cosine of negative 1,000 degrees is the same as the cosine of positive 1,000 degrees. You can drop the minus out from the angle. But for any of the other trig ratios that isn't cosine or secant, if I had the sine of negative 120, it would not equal positive the sine of 120. And let's see why. Let's do a slightly different one. Let's do the sine of 135 degrees. (135 degrees goes into quadrant 2. This is 135 degrees. That's theta. Theta bar is therefore 45 degrees. Well, theta bar being 100, we're doing sine of negative 135. My bad, people. Erase this. Because we're testing f of minus x. So negative 135 degrees ends in quadrant 3. Theta bar is going to be 45 degrees still, but end in quadrant 3. So my reference triangle has a 45 degree angle. 45, 45, 90 is proportional in terms of x root 2. So the sine of negative 135 degrees would be equal to the sine of the reference angle in the third quadrant, but in quadrant 3, all students take. Only tangent and its reciprocal cotangent are positive here. So sine would actually be negative in quadrant 3. It's equal to minus the sine of 45 degrees. And the sine of 45 degrees is x over x root 2, so it's minus x over x root 2, or minus 1 over root 2. So the sine of negative 135 degrees is minus 1 over rad 2. If I were to simultaneously find the sine of 135 degrees, positive 135 degrees, well, 135 degrees ends in quadrant 2, still giving me a 45 degree reference angle, but all students, sine is positive in quadrant 2. So my result here would be positive 1 over rad 2. So as we see here, sine of negative 135 doesn't equal sine of positive 135. It is not an even function. Minus 1 over root 2 doesn't equal 1 over root 2. But sine of minus 135 does equal negative the sine of 135. Because the sine of 135 is 1 over root 2. If I multiply that result by a negative 1, I'll get negative 1 over root 2. So we see that sine of x follows the f of minus x equals minus f of x rule, so it's an odd function. So it's useful to note we had implications for the graphs as well when functions were even or odd, but we don't really worry about the graphing implications here. It's much more so interesting when we get into the trig proofs. You're gonna really be tested on these types of things within calc. If I have the sine of a negative angle, how would that impact? If I had the cosine of a negative angle, how would that impact the ratio that you were given? So basically, long story short of it, you have it all on the slide here. The sine of a negative angle would be minus the sine of the positive angle, for instance, because sine is odd. The cosine of a negative angle, we can just drop the negative sign. It's the same as the cosine of the positive angle. They're the same, because cosine is an even function. So those are the main implications for 5.1 and 5.2. Again, guys, try the homework problems, try the whiteboard problems, and reach out to me if you guys have any issues. Take care.